Hi there, and welcome back. I think it's going to be a good time to talk about marks. So, what is a marks? Well, we can think about the marks as something that takes some input and gives you some output, which is a very extremely general description, actually. So, what is it really? Well, let's suppose that we have 2 to 1 marks, right? So, something extremely simple. So, you essentially have two inputs, which are going to be our I0 and I1, which are going to go into a marks, 2 to 1 marks, 2 to 1 marks. Then we have this register. So this basically this register, which is S0. And lastly, we have the output, which is our Q0. Essentially, this is what we basically have. What's going to happen? Well, in the marks, we can think about Q as the output. So we're going to have a set registry, so set line, and then two inputs, which can be like 0 and 1. So let me show you an example with the 4 to 1 marks, right? So if we have something like a 4 to 1 marks, sounds like this, like I0, I1, I2, they can be many different sizes, and I3. So those 4 inputs. Then what we have here, I1 max, is still one single output, which we call Q0. But now we're going to have two register line, namely S1 and S0. Why do you think that is? Well, in this case, I said that we can think about this as 0 and 1, and this as a set line. So it depends on where it's set. However, in this case, we're gonna think about this as 0 0 0 1 1 0 1 1. We're gonna think about the S1 as 1 and the S0 as 0. So essentially, if we have or S1 as 1 and S0 as 0, as 1, or both of them are 0 and so on and so forth. So for instance, if we have S1 set to 1 and S0 set to 0, then this one is actually going to go to the output. If we have something different like S1 set to 1 and S0 set to 1, then this one is going to go to the output. If we have something else, again, like 0 0, then in this case, I0 is going to go to the output, and so on and so forth. So in this case, instead, it's pretty simple, because if we have S0 as 0, and think this about like almost as if it's a set. So if we have S0 equal to 0, then I0 is going to go to the output. And if we have S0 equal to 1, then I1 is going to go to the output. So that's fairly easy, actually. So you can kind of basically write down all the equation to the max, and you can actually do that using basically considering all the possible inputs. And what you will do will be this. I suppose we have S1 and 0 and I0, I1, I2, and I3, those 4. A table. So we have S. 0, 0, and then we put I0 here, and then 0, 1, I1, 1, 0, I2, and 1, 1, I3. So basically what we're going to do in this case to represent this is saying this, okay, let's suppose that we do have the inputs, and we put as the output, we're going to put those I. So we can basically write the equation just like we were doing for, regular tables, like the truth table, for instance. So what we're going to get is if S1, so basically our Q0, our final output, it's going to be that if S1 and or S0 are 1, then we're just going to put S1. Otherwise, if they're not as set to 1, we're going to put those as with a big fat knot at the top. And we are basically going to use the sum of product notation, which is basically the one of the mean terms. So if I'm going to write this in terms of, mean terms, just like I did, when I was using mean terms with the truth table, I will say, okay, so S1, when S1 is 0, so S1 naught times S0, S0 is 0, so S0 naught times I0 plus, this is a product of, the sum of products, form for the mean term. So S1 is 0, so again, you get S1 naught times S0 is 1, so this time we're going to get S0, we're going to get times I1 plus S1 is 1, so we're going to get S1 times S0 is 0, so S0 naught times I2. And lastly, we're going to have S1 as 1, so S1 times S0, which is 1, so times S0, times I3. So this is basically our kinda of mean term notation for these 4-1 mux, which takes 4 input which you register, and it basically outputs only one thing, which is Q0. We have basically got the expression here of those. So this is the equation. It's basically showing that basically showing you the output. Basically, we can have other kind of mux. We can have even bigger ones, like for instance an A21 mux, where we have things like I0, I1, I2, I3, I4, I5, I6, and I7. Yeah, sorry for my bad handwriting. Anyway, gotta stick with it, I guess. So this is an A21 mux, which basically outputs Q0. But in this case, I'm gonna have not just 1 as 0, not just 2 as 0 as 1, but 3. So 3 registry line. So S2, S1, and S0. over here, because this is an 8 to 1 mux. So we actually need 3 address lines because we need 3 binary digits to represent 8 different combinations. And therefore, we're going to use that. What it can actually be used for, I mean, this whole thing about the mux, you are probably wondering, okay, fair enough, I can understand that, but why is it useful? Well, it's useful because, first of all, most of the time is what you're going to have, like even in real life, you're going to have a mux with, you know, a certain amount of inputs, and also and address lines and a certain output. So you're kind of have to, you know, learn about it and deal with it. But most importantly is that whenever you are designing, Maxis can actually help you to design, you know, pretty fast, to be fair, compared to, you know, the doing the normal, you know, K map and other things. If you have a Max, you don't actually need to do much work, because, for instance, you can basically map those to some things like let's just make an example to clarify this and just show you why it's actually very, very useful for design. Let's suppose that we have, I don't know, some kind of values like, I don't know, like 0, 1, 0, I don't know, 1, 0, 0, and then 1, 1. And let's suppose that we have some kind of thing like A, B, and C. And let's suppose that we want something like, I don't know, let's suppose we have a table again, where we have A, B, C, and then we have the output Q. Let's suppose that we want, well, when A0, B0, C0, we want the output to be 0. Well, I can just basically assign, if I have assigned I0 as 0, I can say, okay, when A is 0, B is 0, C is 0, then the output is going to be I1, which is fixed at 0. If we can do that and say, okay, if A is 0, B is 0, C is 0, then I'm just going to have I0 going to the output. Again, if I have, I don't know, like 0, 0, 1, I'm going to have 1, let's say. Well, in this case, I can say, okay, fair enough. I'm going to have A is 0, B is 0, C to 1. I kind of need a 1. Then I'm going to say, okay, this I1 is actually going to go to Q this time. So I'm going to choose I1 to go to Q. So it's actually, you know, it's pretty straightforward and easy to kind of decide where things are going to go, and you know, to actually design something, because, you know, you have a max, it's way easier. And you just, you know, you can just put the, you can do pretty much everything with a max. And this is not even the best way to do that. You can actually simplify it even more, because, you know, let's suppose that let me just do that with K-map, right? Let's suppose that we have a certain K-map where we have 0, 0, 0, 1, 1, 1, 1, 0, and then you have, whoops, 0, 0 with a gray code. 0 1 1 1 1 0, and this is kind of your map. Like this. And like this, like this. And suppose we have AB here and CD here. And let's suppose that we have something like, I don't know, well, some values in here inside the kernel map. So basically, in this case, we're going to have A, B, C, and D, which, sure, I can put some value in here and basically make a circuit. But let's suppose that we only have an A21 max. As you can see, there is kind of a problem because we have A, B, C, D in the kernel map with some values, but we only have A, B, and C in our max. So what do we do? Well, first of all, let me just put some value in here. Let me just put something like 1, 1, 1, perhaps 0, 0, 0, 0, no, 0, 1, 0, 1, 0, 1, and then a couple of 0 here. Yeah, let's suppose that we are going to have something like this. So what I'm going to do basically is going to assign the variable to the input. So S2, S1, and S0 are going to be assigned to A, B, and C, just like I did before. But I don't have D. So what I'm going to do is that I'm basically going to make groups so that let's suppose A, B, and C is 0, 0, 0. So let's suppose it is that, and it's going to select input 0, okay? And input 0 is going to go to the output. So when it's selecting input 0, here, 0, 0, 0, 0, I basically have this case and have to select between an output of 1 and an output of 0. And what you can basically see is that the final output is just the inverse of D, because when D is 0, the output is 1. When D is 1, the output is 0. So what I'm going to do is that I'm going to assign D naught to the value. And I can move across all the possible 1. So in this case, I'm going to put D here. 0, 1, 0 is here. So again, D complement. 0, 1, 1 here. So it's D complement. If we have here this one, so 1, 1, 0 in here, the output is just going to be 1. It doesn't really matter what it's going, I'm sorry, here, what it's going to be. And here is 0. And in this case, we have D naught, and here we have 0, 0, so it's just gonna be 0 all the time. So this is basically how you can use a mux as a design block, and it's actually kinda useful to do that, because in this way you can actually solve a lot of things and also save some circuitry, because it will take in more to deal with the schema in which you have A, B, C, and D, but we did that without even needing, a D here. So, mux, when you use the use of a mux can actually, speed things up and help you whenever you have to design your circuit. So yeah, in the next video, I'm going to talk about Dmux because this is just half of the story.